All right, welcome back to The Explainer. Today, we're doing something a bit different and honestly, a lot of fun. Our goal is pretty clear. We are going to upgrade our data BS detectors together. Look, we live in a world that is totally obsessed with numbers, but let's be real, mathematical precision is completely, utterly useless without data integrity. If your foundation is flawed, the most sophisticated algorithm in the world isn't going to save you. It's literally just going to help you arrive at the wrong conclusion faster.
You know, you've probably heard this classic quote. People usually attribute it to Mark Twain or Benjamin Disraeli. There are three kinds of lies: lies, damn lies, and statistics. It basically sets the perfect cautionary tone for everything we're about to dive into today. Because human brains are incredibly vulnerable when confronted with statistics. We just kind of suspend our critical thinking the second we see a neatly formatted chart or a decimal point. But as you'll see, liars use numbers all the time, and it's our job to spot the deception.
And hey, this is definitely not a new problem. Back in 1864, Charles Babbage, the genius who designed the very first digital computer, was asked a genuinely baffling question by members of parliament. They essentially asked him, hey, if you put the wrong numbers into the machine, will the right answers miraculously come out? Seriously. Babbage was just absolutely stunned by the confusion of ideas that could even provoke a question like that, because a machine, no matter how insanely powerful it is, simply cannot cure bad data.
So here is our detectives training manual for today. We're going to run through 5 major traps: garbage in, garbage out, the illusion of summaries, surviving the sampling bias, machine learning mirages, and finally, significance versus practical utility.
Okay, let's kick things off with trap number 1, garbage in, garbage out. This is the absolute foundation of computing. To really grasp the gravity of this, let's rewind to a purely mathematical case study from the deeply flawed 1840 U.S. Census. So during a time of intense national division, politician John Calhoun used census data to make this astonishing claim. He argued that freed black individuals in northern states suffered from dramatically higher rates of mental illness than enslaved individuals. But when former President John Quincy Adams actually dug in and exposed that the data was severely corrupted, like towns had mistakenly recorded mentally ill white citizens as black or listed populations that literally didn't exist, Calhoun defended the data anyway. He falsely claimed that because there were just so many errors, they would simply balance each other out. He was making a fatal mathematical error here. He confused random, unbiased errors that actually do cancel out with volume with systematic, structural bias.
And this comparison brilliantly illustrates exactly why Calhoun had it all wrong. Think about unbiased random error, like an astronomer measuring a star. Sometimes their measurement is slightly over, sometimes slightly under. If you take enough samples, the mean naturally centers right on the true value. But then you have systematic biased error. When data collection is structurally corrupted or manipulated, it shifts the entire distribution. The errors absolutely do not cancel out. Aggregating bad data doesn't magically fix it. It just gives you a highly precise, fundamentally bad answer.
Moving right along to our second sin, the illusion of summaries, or why seeing is believing.
Let's look at how summary statistics can flat out lie to you and how visuals can manipulate. Imagine an analyst hands you a report covering 4 distinct data sets, and they give you these summary statistics. The mean of X is 9.0 for all of them. The variance is identical. The correlation coefficient is perfectly matched. I mean, if you only looked at these identical summaries, you would be totally lulled into a false sense of security, assuming the underlying data was exactly the same across the board. But then you get to the visual reveal, and wow. This is known as Anscombe's quartet, put together by statistician Francis Anscombe back in 1973. Despite having identical math in their summaries, the geometric shapes of the raw data are wildly, unbelievably different. You've got a standard linear relationship, a smooth nonlinear curve, a tight line with one massive outlier, and a vertical stack. It's crazy, right? This proves an absolutely crucial rule. You must always plot your raw data before trusting a statistical summary.
But wait, even pictures can deceive you. Take a look at this mathematical deconstruction of a welfare chart that was actually broadcast on Fox News. In the first version, the baseline of the y-axis has been truncated so it starts at 3.90 instead of 0. Mathematically, this truncation artificially magnifies what is really just a tiny 2.5% variance into a massive, exaggerated 2-to-1 visual spike. When you look at the honest axis starting at 0, it reveals the actual minimal variation. The takeaway? Always check the axes. Always.
Okay, that brings us to number 3, surviving the sampling bias and dealing with hidden filters.
So a huge part of being a data detective is knowing that what you don't see in a dataset often matters way more than what you do see. Let's test your intuition with a famous historical riddle. During World War II, military analysts were looking at returning bomber planes that were absolutely covered in flak holes. They meticulously mapped out exactly where the bullet holes were located on the fuselage and wings. So, based on this observed damage, where would you place the extra heavy armor to reinforce those planes? I mean, it seems super obvious to just put the armor where all the holes are, right? Actually, no, wrong. Statistician Abraham Wald uncovered a brilliant, counterintuitive truth here. You armor the places with 0 bullet holes. Why? Because the planes that got hit in the engines never survived to make it back to the runway. The analysts were falling hard for survivor bias, reaching faulty conclusions by exclusively analyzing data that successfully passed a hidden selection process while completely ignoring the missing, lethal data. And we see this exact same flaw today whenever we substitute true random sampling with convenience sampling. Whether it's a political poll that only calls landlines, totally ignoring an entire generation of mobile users, or university course evaluations where all the struggling students already dropped out, convenient sampling just ruins the underlying math. Drawing a convenience sample creates a deeply skewed distribution. And gathering more data in this scenario, it doesn't help at all. It simply increases your statistical precision around an entirely incorrect mean.
All right, stepping into the modern era with number 4, machine learning mirages and the black box illusion.
So we really need to break down this illusion of AI objectivity, especially the hidden dangers lurking inside high-dimensional predictive models. When a machine learning model is given hundreds or thousands of features, sometimes nearly as many as the data points themselves, it just stops learning true patterns. Instead, it just starts memorizing random noise. We call this overfitting. To control this chaos, data scientists use mathematical penalties called regularization, specifically L1 or L2. These penalties act like a leash. They artificially shrink or completely eliminate the weights of redundant features to force the model to actually generalize better.
To see why you can't just blindly interpret a model's inner workings, let's look at a logistic regression model predicting survival on the Titanic. Think about the cabin classes. They are mathematically correlated. Everyone has to be in exactly one class. If you are in first class, you are definitely not in second or third. Because of this inherent correlation, evaluating these feature weights in isolation is an incredibly dangerous game. And this brilliantly illustrates the mirage. In the original model, you see one set of weights. But the literal second we eliminate the first-class variable from the math, look at what happens. The remaining class weights violently flip from positive to large negative values. The model's overall accuracy didn't change at all, but its internal story completely reversed. Feature correlations hide the truth, which basically means you can rarely look at one variable's weight in an AI model and just confidently declare it the defining cause.
Which brings us to our final stop, number 5, significance versus practical utility, where we deconstruct the ROC curve.
For our final statistical sin, we have to talk about the massive, often totally misunderstood gulf between a finding being mathematically significant versus it actually being, useful in the real world. When evaluating how good a model really is, picking a single arbitrary cutoff point can be super deceiving. Instead, we use the receiver operating characteristic, or ROC curve. Think of a dotted diagonal line as a completely random coin flip. The curved line above it is our model. What we really truly care about is the total area under that curve. The closer that area is to 1.0, the closer we are to a perfect classifier.
But here is the major catch, and analysts exploit this all the time. Statistical significance simply means we have high mathematical certainty that a result isn't entirely random. That's it. Practical utility, on the other hand, means the model actually makes useful, profitable predictions out in the wild. The secret is that as your sample size grows towards, say, 1 million records, your standard error mathematically plummets towards 0.
This comparison makes it perfectly clear. On one side, we have a model tested on 1 million data points. It is officially crowned statistically significant with a p-value of less than 0.001. But look at its curve. It is almost identical to a random coin flip. It offers literally 0 real-world value. Then, on the other side, you have a model that actually provides practical utility, achieving a robust, healthy area under the curve. Never, ever let someone sell you on statistical significance without showing you the actual practical utility.
Well, we've covered a ton of ground today, haven't we?
From the fundamental law of garbage in, garbage out, to the visual deceptions of truncated graphs, the hidden filters of survivor bias, and those tricky mirages of machine learning, you are now officially armed with a finely calibrated BS detector. So I'm going to leave you with this final, provocative thought. The next time you see a bold, data-driven claim on the news or pitched in a boardroom, ask yourself not just what the math says, but what aren't they showing you? Keep questioning, keep learning, and I'll catch you in the next explainer.